Good afternoon, dear colleagues. We invite your attention to a report on the topic, a problem of managing the reserve of capacity for the arcs of a communication network. We consider the problem of managing the reserve of capacity of arcs, which is relevant for the distribution of flows and designing reliable communication networks with discrete parameters and a constraint on flows, delay time, or average load factor of the network arcs. See Works 1-2. An algorithm for the approximate solution of the problem for the case of linear functions for the cost of arcs is proposed, and the results of its experimental study on a network containing 1,000 nodes and 4,000 arcs are presented. The results of the experiment showed the sufficient accuracy and speed of the proposed algorithm, which allows us to assert of its practical applicability for engineering calculations on the large-dimensional networks. The formulation and algorithm of solving the problem: we consider a direct connected network with a set of nodes and a set of arcs. In network, for each direct arc exists back arc. An arc represents a switched communication line in a data network or a vehicle route, the final nodes of which coincide with the initial and final node of the arc. The network may contain loops and parallel arcs, since cyclic and repeating communication lines and communication lines with the same final nodes are allowed. An integer flow matrix U is given on the network. Let WKL sort for a bandwidth capacity of arcs of the network in transport blocks, ascending positive integers DKL, arcs lengths. CKL, discrete values cost of arcs, such that CKL, Y DKL, less or equal CKL, Y plus 1, DKL, FKL, to fix total flows in transport blocks, are flowing along the arcs of the network, where UIJKL is the flow of transport blocks from I to J, which passes along arc KL. It is required to find the minimum value of the network cost function set to for the parameter of selected values that vary within the following limits, where to estimate the bandwidth reserved for each solution, we will calculate the average load factor of arcs for the network. Note that problem 1.2 can be represented as a knapsack problem with Boolean variables and multi-choice 0 to 1 multiple-choice knapsack problem 0 to 1 MCKP, which, as you know, belongs to the class of NP-hard problems. For the knapsack problem with multi-choice, there are exact pseudo-polynomial algorithms and fully polynomial time approximation scheme (FPTAS). This means that for them there are algorithms that polynomial time of the size for the input of the problem and make it possible to obtain a guaranteed approximate solution, where is an arbitrarily small positive number. Therefore, to obtain an accurate or guaranteed approximate solution to problem 1.2, it is possible to use these algorithms. Despite the existence of exact pseudo-polynomial algorithms, their application for the parametric solution of the PCCA problem is not justified due to the great time complexity of the algorithms. So, for example, the time complexity of the FPTAS algorithm for solving the classical 0 to 1 MCKP problem is N3 for solving NP-hard problems 1.2. Two approximate algorithms were proposed on the basis of the approximation of discrete cost functions by linear ones, and on the method of sequential analysis of options. By controlling the parameter Tmax for maximum delay, the data network administrator or the transport network manager can provide the required reserve for the bandwidth capacity of the communication channels or the carrying capacity of vehicles at predicted fluctuations of values of flows on a given time of intervals. A decrease in the parameter, increase in the reserve, leads to a rise in the cost of the network, but reduces the probability of redistribution of flows and technical re-equipment of communication channels or fleet of vehicles at increasing flows and a threat of emergence overloads in the network. An increase in the parameter makes it possible to reduce the capacity of communication channels or the carrying capacity of vehicles and the cost of the network, but increases the risk of redistributing flows and upgrading the network. As a quantitative measure of reserve capacity can be taken as the average load factor of the network arcs. Algorithm of solving the problem. We consider problem 1, 2 when it is known that a given discrete value's cost of the arcs can be approximated with a sufficient degree of adequacy by continuous linear functions where we found approximation coefficients. For linear cost functions, the analytical solution, which is obtained by the method of Lagrange multipliers, is known. The approximation algorithm allows one to quickly get into the neighborhood of continuous points optimum of and find an approximate discrete solution. We present a general scheme of the greedy algorithm for the parametric solution of problem 1, 2 for linear cost functions. The idea of the algorithm is as follows. Suppose that for all arcs the coefficients of the linear dependence 9 are known. Such coefficients can be obtained for each arc KL of length dKL by linear approximation, for example, by the least squares method of discrete values cost of the arcs for a number of standard discrete capacity, the same for all arcs. Knowing the coefficients CKL1 equals TG, see the Fig. 1, and the values of through formula 10, you can find the throughput. Next, in the neighborhood of continuous optimums according to a certain procedure, we select the suitable carrying capacity values from a discrete range. In Fig 1, we see the cost function of arcs results of the experimental solution of the problem. The problem was solved by using an example of a network with equals 1000 nodes and equals 4000 arcs, generated by a pseudo-random number sensor. The lengths of arcs ranged from 20 to 50 kilometers, and values of flows from 1 to 2 transport blocks. The values were obtained by distributing all flows along the shortest paths using the two criteria lexicographic algorithm. 18. The throughput of arcs was selected from the set 5, 10, 15, 20, with a sampling step of 5 units. The cost of arcs for a given set of throughputs of arcs was calculated by the formula for linear functions. The coefficients were chosen from the sets 0, 0, 0, 0, 0, and 5, 10, 15, 20. The number of values in the set Fig was determined depending on the maximum flow along the arc, the sampling step of the throughput capacities of the arcs, and the initial value. If for the current value of it turned out to be, the set can be automatically expanded to the value where is the rounding sign to a larger integer multiple of 5. The table 1 shows the results of solving the problem when changing constraint at the delay time from e equals 0.00 to e equals 10.0. For all values of the parameter, the following are given: continuous optimal solutions, rounded to integers, and approximate discrete solutions, as in nominal units of cost value. Values of the average load factor of arcs for network, alpha deviations in % of approximate solution from the continuous optimal solution, as it is visible in Table 1. Continuous optimal and discrete approximate solutions are differing slightly with a value from 0.0032% to 0.0796%. In a variant of solution 33 it equals 7.0. The lower boundary of the network cost 378,295,008 is reached, which cannot be improved at the further increasing the value of. It follows that the deviations of discrete optimal and approximate solutions will be even smaller. The most interesting variants for analyzing and deciding the choice of reserve for the capacity of arcs are the solutions with numbers 1 to 12. for which the network cost is significantly reduced by 308,476,576 units, and load factor of ARCs is increased from 0.39 to 0.91. These variance solutions are clearly shown in Fig. 2. The same results as in Table 1 were obtained when solving the problem with an approximate algorithm on the basis of the method of sequential analysis for variance, which is given in 1. However, the time complexity of this algorithm is several orders of magnitude greater, and to calculate each solution for the given values, it took from 5 to 12 seconds on a PC with a clock frequency of 2.66 GHz. The app algorithm coped with such tasks in a split second. In Fig. 2, we see a change in network cost and load factor of the ARCs from Tmax. The values in the is line is multiplied by 109. The experimental results were obtained on a dual-core PC with a clock frequency of 2.66 GHz and 2 GB RAM under Windows XP. All programs are written in software environment Microsoft Developer Visual Studio. Conclusion: the article formulates the problem of managing the reserve of capacity ARCs in a communication network with discrete parameters when changing the constraint on the delay time of flows. An approximate polynomial algorithm for solving the problem for the case of linear of ARCs cost functions is proposed, and the results of its experimental study are presented. The experimental results allow us to state the practical applicability of the algorithm for solving the problem on large-dimensional networks containing more than 1,000 nodes and 4,000 ARCs. Thanks for your attention.